the main flux. Let us assume that this is the main flux, or else the flux emanating from the primary. And because of this closed path current delivered, because of that flux delivered, this flux developed or induced in the secondary coil is trying to oppose the flux emanating from the primary coil, according to Lenz's law. Now you know the direction of the flux. Yes or no? Now, if you know the direction of the flux according to right-hand thumb rule, can't you find the direction of the currents using the same right-hand thumb rule? You see, this is downward as far as this coil is concerned, the flux. Now this is opposing. Therefore, hold the coil again by stretching your thumb. The thumb is indicating the flux. Now the fingers are indicating the current. It is simple. You're holding the coil like this. The upper portion of the coil you are able to see like this. Now obviously the current is flowing like this, means it should come from here, then only it is possible like this. That's it. This is leaving. And identify the terminal where the current leaves and put a dot there. The whole story, what we have implemented is just to identify the dots. Understand all of you? Once the dots are identified, I can take like this. I can draw now the magnetic coupled circuit, dot and dot. Understand all of you? Okay. Now this magnetic coupled circuit you can use anywhere that you want. But the relation between these two coils is always indicated by these two dots. Understand all of you? Okay. So based on these dots, then you have to go for the self-induced EMF and mutual induced EMF, and mutual induced sign can be easily decided based on the dots. I hope you understand the point here. Okay. Let me take another example here. You will understand clearly. See this? I hope you understand. This is the primary coil. First select any one of the coils. Okay, I selected this. Put a dot where the current enters. Assume that some current is entering here, then dot. So this current is flowing like this. Yes or no? Now it is leaving from this. Now stretch the fingers along with the current direction and hold the coil, and thumb is indicating the flux. The flux is flowing now like this. Because of this flux emanated by the primary is flowing like this. But now I told you already, once you close this and make some current flow, and already EMF is available, because of that some current flows when you close it, and flux is developed by the secondary coil. That flux will try to oppose the flux emanated by the primary coil. Now that's it. As far as this coil is concerned, what is the flux direction? This way. Now hold the coil. Now this is what the non-magnetic core, I'm taking it out. Now I'm holding. You understand? I'm holding. Understand all of you? Okay. Now the fingers are showing what? The current direction. Where are the fingers? How they are covering? In the lower part or upper part, you can see. Understand all of you? Okay. The lower part, the coil behind this particular non-magnetic core, when you hold the coil, okay, this is what the direction of the currents. So downward. Upward in the lower portion, but downward in the upper portion, which is visible to us. So now where is it leaving? Now this is entering, this is leaving, and this is the dot. Clear all of you? Okay. Now you got the relation between these two. This is how you can easily identify. Simple step you can remember. First select, put a dot and direction, then hold and flux. And this flux opposes. Now hold the coil. Having known the flux direction here, you can identify the current direction. Now identify the terminal where the current leaves. Put a dot where the current enters and identify the terminal where the current leaves and put a dot. So in the secondary coil. It's as simple as that. Okay. Of course, in most of the times in exam, generally, directly this kind of diagrams will be given with the dots. You don't need to work, but we don't know. We can't predict because gate is completely unpredictable. Understand all of you? Okay. And in any competitive examination, there are no boundaries for the questions. Sometimes he will give you this. Understand all of you? Okay. And he will ask you the questions based on this. So unless you know the dots, you cannot solve the problem. And unless you know how to create the dots, you can't put the dots. Please note down. Please note down. Meanwhile, I just remove this part. Mesh equations. You can write only mesh equations in case of magnetic coupled circuits. Node equations is not possible. In magnetic coupled circuits. Let me take an example of it. R2, L2, L1. Here are the dots, let us assume. Mutual inductance is M, let us say. This is R1 excited here, plus minus V1 of t. Now the mesh currents are given like this. This is I1, this is I2. Equations can be written in two different forms. Okay, equations can be written in two different forms. One is the time domain or instantaneous. The other is RMS or complex. Or phasor form. People call even phasor form. Okay, so first let us write time domain, then we can go for complex RMS. You already know that V is equal to L di by dt. If you can write time domain, how do you write in complex? Capital V j omega L into. Agree all of you? V is equal to 1 by c integral I dt. How do you write? Capital V is equal to 1 by j omega c. Yes or no, all of you? 1 by j omega. 1 by j omega. Yes or no, all of you? Into I. This is how you write time domain and complex. Time domain and complex. That's what we are going to do here. So time domain, when you write loop 1, V1 of t, okay, minus I1 of t into R, minus L1. Yes, self-induced EMF, there is no need to look at any other dots and all. Okay, directly you can write minus L1 di1 by dt. Okay, so you got this self-induced EMF sign because I'm following the convention called fallen voltage negative, rise in voltage positive. People who follow the reverse convention, like rise in voltage is negative and fallen voltage positive, they may get plus here. So therefore self-induced EMF sign identification is not a problem. Now you need to identify the mutual induced EMF. So this is the self-induced EMF, you already got it. But there is one more EMF induced in this one, that is called mutual induced EMF. This is E1, you already got, but E1 dash, that is because of current flowing through the secondary coil. Yes or no, all of you? Okay. So what is that? M into di2 by dt. Yes or no? But what is this I1 doing entering at the dot? What is this I2 doing entering at the dot? When both the currents are entering at the dot, what is that we have actually seen in the previous cases? Okay, the mutual induced EMF sign is same as that of self-induced EMF. Understand all of you? Now you tell me flux aiding case or flux opposing case. Which one are you getting here? Flux aiding or flux opposing? You are getting flux aiding. Whereas in the case 2, you see, we have seen already that case 2 E1 total is minus E1 plus E1 dash or plus E1 minus E1 dash. Okay. This particular case, what is happening? Flux opposing case. Flux opposing case. Yes or no, all of you? If you have written, okay. Otherwise, you write there itself. Where we have indicated the dotted, dot convention method, we have taken two cases. Now here, V1 I1 R minus L1 di1 by dt minus M di2 by dt, and anything else left over 1, 2, 3 plus mutual induced 1, 2, 3, 4, total 4 terms. equals 0. Equation. This is in time domain, but if you go for a complex, you know that capital V1 minus capital I1 into R, RMS completely. This is time domain, instantaneous, minus j omega L1 of what? I1 minus j omega n, it is also in Henry's, into I2 is equal to 0. That's it. Look to, you can write, tell me, plus V2 of t minus R2 I2 of t minus L2 d I2 of t by dt. See, this is the self I can write easily. But mutual again, M d I1 by dt, the EMF induced in this, there are two EMFs here. One is self, the other is mutual. Self I have written already. But what is the mutual induced EMF in the secondary coil? It is the EMF induced in the secondary coil due to the current flowing through the primary coil. Okay. So therefore, M into the current flowing through the primary coil is I1, and this current is entering, this current is also entering, same sign, minus is equal to 0. Complex form. What is the complex form? Capital V2 minus R2 capital I2 minus j omega L2 into I2 minus j omega n I1 is equal to 0. So once you know the complex form, you can go for Cramer's rule and simplify what is I1 and I2. Once you know I1, I2, anything that you want, you can calculate. Understand all of you want to find current, voltage, power, anything you can find. Please note down that quickly, all of you. Let's take some important points. Put a note. Number 1. So this is a transformer. Primary turns N1 and this is N2. Say the dots are already defined or given. Okay, all of you. But the dotted terminal is always assumed to be a higher potential with respect to the other. Understand all of you, okay? Say the polarities of the voltage are given like this. What is the actual polarity? Dot is supposed to be at higher. It is also given dot. What is the terminal here? Dot is at higher. Okay, it is also given at higher, let us assume. So it is what actually desired. Yes or no, all of you? This is desired, so it is available. Current always flows from higher potential to lower potential. Yes or no? It should flow. Assume that given as, okay, I1. Current should always flow from higher potential to lower potential. If you connect a load here, okay, how does the current flow? In this direction. Why? Because higher potential. Why it is higher potential? Because dot is available here. Therefore, so this is a standard case using which you can find the remaining cases. You have to understand this particular concept. Okay. So with this, you know that V2 by V1 is equal to N2 by N1. And I2 by I1 is equal to N1 by N2. Clear all of you? That is the ratio. Okay. This ratio can also be called as N, small n, or small k, let us say otherwise. Turn ratio you call it. What is K? Turn ratio. You call it turn ratio. Second case, let us observe. What is the second case? Second case, now with respect to first case, you can easily find the relation between V1, V2, N1, N2. This is plus minus V1. Dot is here. Here is a dot. But here is given minus plus V2. It is supposed to be plus, but the polarities are given minus plus. The current is supposed to flow from higher to lower. Okay, it is flowing. The current is supposed to flow from higher to lower because this is at higher potential. Therefore, I2. That means it is entering into dot. This is leaving from dot. Understand all of you? Okay. Well, but what is actually happening here is the polarities of the voltage across these two terminals is supposed to be plus minus because the higher potential. But you are measuring the voltage with minus plus. See, the actual voltage polarities is plus minus. But the desired polarities are what? Minus plus. The actual polarity is what? Plus minus. The desired polarity, that means you are connecting the voltmeter with plus minus only. Therefore, there is no problem. Understand all of you? Okay. That is why you got plus only. But now here, V2 by V1. Actually, this is now plus minus minus V2 it becomes. Yes or no? Therefore, finally V2 by V1 can be written as minus N2 by N1. And there is no change in I2 by I1. That is N1 by N2 only. Because I1, I2 are not affected here. Okay? Only V2 is affected. I2 is not affected. Third one. What are the actual polarities? Plus minus. But how you are measuring the voltage using the voltmeter? Plus minus. No problem. Here also plus minus V2. How the current is supposed to flow from higher to lower? When you connect a source here, current flows from higher to lower. This direction it is supposed to flow. Okay, it is also given this direction. And when you connect the load across it, current flows from higher to lower. This direction is supposed to flow. But now it is given I2 like this, let us say. The actual current direction is supposed to be like this because this is positive terminal, this is negative terminal. When you connect the load, higher to lower it is supposed to flow. But the ammeter is measuring reverse current. Yes or no, all of you? That means if you change the direction of it with respect to this, if you want to compare, it becomes now I2, then this becomes now, if you indicate in the same direction, it becomes minus I2. Then you get the relation. That means minus I2 by I1 is equal to N1 by N2. Finally, I2 by I1 is equal to what? Minus N1 by N2. So, V2 by V1, there is no problem, N2 by N1. But I2 by I1 will become what? Minus N1 by N2. That's it. Clear all of you? Fourth case, you can see. Fourth case. Fourth case. This is the actual polarity plus minus, but how he is measuring using the voltmeter with the same polarities. This is supposed to be plus minus, but how you are measuring the voltage? Okay, say minus plus V2. The ammeter is supposed to be connected plus minus because current flows from higher potential to lower potential. This is the direction, that means plus minus. That means I1. The ammeter is supposed to be placed to measure the positive current because this is higher potential and this is a lower potential. When you connect a load across it, higher to lower the current flows this way. But the current is shown reverse. The actual is this, but we want in this way. The actual is plus minus, but we want with minus plus. So what will happen here? V2 by V1 is minus N2 by N1. I2 by I1 minus N1 by N2. All these I am comparing with this only. I repeat once again, this is a first case. Okay, benchmark case. The dots are showing always at higher potential with respect to the other. Agree all of you? This is a dot at higher potential. That means this is plus, this is minus. These are the actual polarities. But how you want using the voltmeter also plus minus. Good. Current always flows from higher potential to lower potential. This is higher, this is lower, shown by this. supposed to be like this, it is also like this. That means ammeter is also placed proper. Now, this is higher potential, actual polarities, desired polarities using the voltmeter also you are measuring the same, plus minus. Current always flows from higher potential, lower potential. When you connect a load across it, the current should flow like this. It is already flowing like this. Okay, so the currents are shown as available, the directions, and polarities are indicated as actual. The desired is same as actual. That is why you got this case. With respect to this, the remaining three cases are derived. Please note down that. Let me remove this part. Hope you finished this, right? So first we see the cases, okay? Then important concepts, important cases, then we go for the numericals. Once you understand this, the numericals are very simple, okay? So another important part of it, I would like to replace this magnetically coupled circuit by only conductively coupled circuit, no inductively coupled, equivalent. Say this is the T model, LA, LB, LC. Okay, I want to replace this by its equivalent conductively coupled circuit. Okay, so this is L1, this is L2, this is M. Now this is an equivalent of this. That means the equations of this and the equations of this you can derive and you can compare. Yes or no, all of you? Because both are equivalent. Say this is V1. To get the relation between LA, LB, LC in terms of L1, L2, M, what I do is I obtain the mesh equations here and I obtain the mesh equations here. Then I'll compare. Then I'll get the automatically the relation. Agree, all of you? Okay. So let me proceed like that. So this is V1. This is I1. This is V2. This is I2. Similarly, here also V1, I1. Say this is I2. This is I1. So what are the equations you get here? Tell me. Let me write in complex form directly. The equations, mesh equations. What do you get? when you write the equation, V1 minus j omega L1, yes or no? V1 minus j omega L1, self-induced EMF, but mutually, that is M D, this is not in time domain, this is in complex. J omega L1 into what? I1, you are getting. Agree? Then here what? J omega M into I2. Current is entering, same sign. This is minus, therefore this is also minus, is equal to 0. Agree all of you? Okay. Now from this, I can write V1 is equal to J omega L1 into I1 plus J omega M into I2. First equation. What about the second equation? This is the loop 1 and the loop 2. Second equation, please. Capital V2 minus J omega L2 into I2 minus J omega M. Why minus J omega? Because self-induced EMF and mutual induced EMF, when you compare, the self-induced EMF sign is minus. Since current is entering and here also entering, same sign you are supposed to take. Current flowing through the other coil. Okay? Is equal to 0. From this, I get V2 is equal to J omega M into I1 plus J omega L2 into what? I2. This is the second equation. So what do you get here from this? From this, you will get, from this, you can write in the matrix form. V1, V2 is equal to J omega of L1, M, L2 into what? I1, I2. Okay, this is called inductance matrix. I just separated J omega, otherwise it will become reactance matrix. Okay, J omega L1 is a reactance, but L1 is an inductance. So this matrix I am calling it inductance matrix. Now let us write the mesh equations for this. If you write, what do you get? Mesh equations. This is I1, this is I2. Shall we use directly the inspection method? You all remember, all of you. But when you write the mesh equations, you must convert all these values into complex. J omega LA, J omega LB, J omega LC. Okay. So V1, let me write clearly. Let me write clearly. What is this? J omega LA plus LC. J omega LC. Okay, this is minus. Let me write once again. Clearly. Matrix form. Sum of all impedances in the first loop. What is that sum of all impedances? J omega LA plus J omega LC. So let me take common, plus LC. Sum of all impedances in the second loop here. Therefore, J omega, this is minus sign, right? Okay, this is minus sign. LB plus LC. How the loop currents are flowing in the common element? Downward, and this is also downward, same direction, same sign as diagonal element. So minus J omega LC. This is same. First row, second column, second row, first column. LC. This is I1, I2. I'm writing in complex form. And this is touching the negative polarity first, therefore minus V1. Touching negative polarity first. Okay? Yes, sir, all of you. Touching negative polarity first, minus V2. Sir, so minus. If you can cancel. Finally, J omega. You also get, this is equation A, let us say. V1, V2 is equal to J omega LA plus LC, LB plus LC, LC LC into I1, I2. This is equation B. Let's compare the matrices. Inductance matrix. Both the matrices when you compare, okay, from equation A and B, LA plus LC is equal to L1, LB plus LC is equal to L2, LC is equal to M. From this we can get LA is equal to L1 minus M, LB is equal to L2 minus M, LC is already M. Yes or no, all of you? Therefore, this is how you can get it. Got it, all of you? Okay. So this is now L1 minus M. This is L2 minus M. This is M. Please note down. So I have converted successfully the magnetically coupled circuit. Magnetically coupled but electrically separated. But I convert that into an equivalent T model of completely electrically coupled, magnetically isolated. Got it, all of you? Okay. So this concept is very important. Wherever you can solve the problems, you want to replace the transformer by the T model, the problems will become easy in most of the cases. Please do that. I can now construct an equivalent delta for it. Understand? You draw it separately again, the diagram. I'm just drawing here itself, but you draw it separately. T model to pi model. So what will happen here? Say this is LC dash, this is LA dash, this is LB dash. So what is LA dash? What is LA dash? LA into LB, LB into LC, LC into LA by LA dash is nothing but what? LB. LB dash is nothing but the same numerator but LA. LC dash is nothing but the same numerator but what do you get? LC. Yes or no? LA dash you will get the other element. LA, LC are involved in this, right? Therefore other terminal. I think all of you remember star delta transformation. I don't want to explain again too much here. If you have any doubts, please refer back to the star delta transformation. What formulas we applied there, it was very clear. So from this, if you simplify, you will get L1, L2 minus M square by L2 minus M. Here also, L1, L2 minus M square by L1 minus M. Here also, L1, L2 minus M square by just M. See, these formulas are valid when you have polarities dot dot here. Suppose one dot is here, the other dot is here, then things may change. Understand, all of you? Okay. Then the formulas will be different. What difference you get? Now M is replaced by minus M. Getting, all of you? Okay. So that is why when you remember the formulas, you should also remember with respect to the dot. Otherwise, you may do mistakes in the exam. Understand, all of you? Okay. For this case, if this is a dot and here is a dot, let us say, then this is L1, L2, M. Now the T model will become something like this. This is LA, LB, LC. And pi model is something like this. LC dash, LA dash, and LB dash. Now the LA will become L1 plus M. LB become L2 plus M. M is replaced by minus. When you compare with this, all the formulas, okay? Now this will become minus. So LC will become minus. LA dash will become what? L1, L2 minus M square. This does not change, but this will become L2 plus M. LB dash will become L1, L2 minus M square by, please note down all the formulas. LC dash will become L1, L2 minus M square by minus. Clear? So this is how you are supposed to convert an inductively coupled circuit into conductively coupled circuit. Okay, now we will see the ideal transform. There are two types of transformers you can see. One is the two-leg transformer, the other is auto transformer. Okay, two-leg transformer we already know, but auto transformer is having only one winding and you will have a tap. Okay, step-up transformer, step-down transformer also we can design using the auto transformer. It's very, very useful concept that I'll come to later. I'll show you how the auto transformer will be. But now let us see the ideal transformer concept. Assume that this is VS1, Z1, and now this is the primary winding. This is N1 is N2. Okay, or else 1 is to N. Anything is okay. Where N is nothing but N2 by N1. Say this is these two are magnetically coupled. This is A and B. This is C and D. And this is now VS2. Getting all of you? Okay. Now N is nothing but what? N2 by N1. If you take 1 is to N, the transformer ratio is given as N2 by N1. But now I am taking for my convenience 1 is to N. That means N is nothing but what? N2 by N1 only, isn't it? But these kind of problems generally can be handled when no inductance is given, only turn ratio is given, and this is an ideal transformer. What is this actually? Ideal transformer. First of all, what is an ideal transformer? Ideal transformer means no leakage of flux. No leakage of flux. No leakage of flux. When there is no leakage of flux, there is no inductance concept. Understand all of you? Okay, there is no inductance offered by this, and no power loss. When there is no power loss, there is no resistor. When there is no leakage flux, there is no reactance or there is no inductance. So the transformer ideal means there is no leakage flux, means no L. No power loss means no R. Yes or no, all of you, power loss is available only, or is happening only when there is a resistive component, I square R loss. So when there is no power loss, there is no R at all. Understand all of you? So these kind of problems generally can be handled by referring the circuit towards the primary or towards the secondary. Okay. So suppose I take the first case, the entire circuit is referred to primary. The entire circuit is referred to primary. When you take referred to primary, usually you know that in case of transformer, you already know this concept. When you have 1:n ratio, if this is V1, this is V2, let us say, what will happen? V2 by V1 is nothing but what? N by 1. What is V1? Okay, V2 by N. That means what? The V2 can be expressed, or V1 can be expressed in terms of V2, that is V2 by N. That means if the voltage on the secondary side is available, is supposed to be referred to primary side, that voltage is divided by what? N. Understand all of you? Okay. Similarly, when you have an impedance, on the secondary side, okay, when you have an impedance on the secondary side, let me remove this clearly, okay. Okay, there is no confusion here. Listen to me carefully. So what is V1, V2 by N? That means when I refer to the primary, then I'll get V2 by N. Understand all of you? When I refer to secondary, then what do you get? V2 by V1 is equal to N. Then V2 is equal to what? N into V1. That means if I refer to secondary, if I just convert all these variables to the secondary side, now that voltage will become what? N times V1. If I refer all this voltage to the primary side, that means you will get divided by N. Understand all of you? Okay. Now, next one is, suppose you have some impedance here ZL. What is this actually? V2. What is the current here? I2. What is the voltage here? V1. What is the current here? I1. I would like to find some input impedance here. I mean, impedance referred to the primary. Look at this. What is Zin actually here? I want to find the impedance referred to the primary. What is Zin? V1 by I1. But already we know that V1 is nothing but what? If this is 1:n ratio, what is V1 is nothing but V2 by N divided by, what is I1 actually here? I1, what will happen here? When you have V2 by V1 is equal to N by 1, what is I2 by I1? 1 by N. Yes or no? Okay. You also know that I1 is N times I2. So N times I2. So V2 by I2 divided by what? N square. But what is this ZL actually here? ZL is nothing but V2 by I2 or not? Agree? Therefore, ZL by N square. So what is proven here? When you find the impedance on the primary side, the impedance seen into the transformer from the primary terminals is observed to be ZL by N square. Secondary side ZL, this is ideal. Yes or no, all of you? This is ideal. No resistance, no inductance of this transformer at all. But when I look into the network through input terminals or primary terminals, I am getting now ZL by N square. That means when the impedance on the secondary side is referred to the primary side, then I got here ZL by N square. Suppose if I take some impedance on the primary available, ZL, and now I would like to find it here, Z out, let us say. If I apply the same concept, what will I get? Tell me. Z out will be definitely N square terms of ZL. If you want, you can see here, this is V2, this is I2, this is V1, This is I1. Yes or no, all of you? But I want Z out to be V2 by I2. But I know already what is V2. V2 is nothing but what? N times V1. This is nothing but 1 by N times of I1. That means N square of V1 by I1. But already what is ZL actually here? ZL is nothing but, I'm sorry, here the direction is given like this, okay? Let me take direction like this. So what do you get actually here? N square times of ZL, because this is nothing but ZL only. So it's very clear, when the impedance secondary side is referred to primary, it should be by N square. When the impedance in the primary is referred to secondary, should be multiplied by N square. Understand all of you? When the voltage is referred to, primary voltage is referred to secondary, okay, then primary voltage is referred to secondary N times. When primary current, similarly, okay, here, when secondary current is referred to primary, it should be multiplied by N. When primary current is referred to secondary, it should be divided by N. So these are the important points to be remembered. Now, an ideal transformer, you have primary quantities and secondary quantities. Primary voltage, primary current, primary impedance. Secondary voltage, secondary current, secondary impedance. Now you tell me what will happen. Now let us all refer the secondary quantities into primary. Now let us refer the secondary voltage to primary. What will happen? Divided by N. Yes or no, all of you? Okay. Current multiplied by N. Current multiplied by N. Impedance divided by N square. This one. Yes or no, all of you? Okay. Now coming to the primary quantities into secondary quantities referred, voltage multiplied by N. Current divided by N. Impedance multiplied by N square. I hope you understand this. So transformer case is very, very clear. Refer to primary, refer to secondary. Now let me summarize all these things. I think you have proven, but I need to summarize here all the points. The circuit is referred to primary, then when secondary voltage, secondary side quantities, will be referred to primary side. Then what do you get here? V2 dash, I2 dash, and Z2 dash. V2 dash is V2 by N. Understand? I2 dash is N times I2. Z2 dash is Z2 by N square. Is it clear, all of you? Now let me take. Refer to secondary. Okay, so refer to primary, V1 remain V1. Okay, I1 remain I1. Z1 remain Z1, no doubt. But the problem is with what? V2, I2, Z2. Now here, refer to secondary, V2 remain V2, I2 remain I2, Z2 remain Z2. But I1 will become I1 dash, sorry, V1, okay? V1 will become V1 dash. What is V1 dash? N times V1. What is I1 dash? I1 by N. What is Z1 dash? N squared times of Z1. It's clear now? Okay. Now this circuit, I would like to work on primary side and secondary side. When I refer to primary, when I refer the given circuit to primary, the primary side, what are the primary terminals here? AB. What are the secondary side? Only transformer you look at. The remaining part, don't worry about that. AB and CD. Now, I'm referring all the components which are connected to the secondary side towards primary. So what is the circuit I'll get here? When this is converted to the primary, okay, referred to primary, what will I get here? Tell me. What will I get? VS1 remains VS1. So this example I have given with an intention that, okay, better we take, I think, the same thing here as it is. Z1, VS1, this is A, this is B. What is the voltage here? What is the voltage available here? V1. What is the voltage available here? V2. Okay. N1, N2. What is the current available here? I1. What is the current available here? I2. Is it clear, all of you? The current available is what? I2. Good. Now, refer to primary. What will happen refer to primary here? This is Z2. But Z2 will become Z2 dash, nothing but Z2 by N square. VS2 dash, VS2 by N. This is nothing but V1. Clear, all of you? Okay. Secondary, refer to secondary then. Once you go for refer to secondary, so the circuits can be easily simplified if you can convert primary to secondary, secondary to primary. But remember, this is possible only when you have an ideal transformer. If you have a practical transformer, you have to convert that into ideal. Okay. Now refer to secondary means CD. This becomes VS2, Z2, but Z1 dash, nothing but N square into Z1. VS1 dash, nothing but N times VS1. This is I1 dash. This is I2. This is I1. This is I2 dash. Note down please, quickly. But what about this I2 dash here? All of you? I2 dash is nothing but what? I2 dash is nothing but what? Primary side you are taking. So generally I1 is equal to N times I2. That means N times I2. Now here you are referring to the secondary, okay? I1 by N. But positive sign or negative sign, how do you take it? How do you take it? Positive sign or negative sign? Entering, it's supposed to be leaving, right? Therefore, it is minus. It is also minus. There is no problem with voltages, yes or no? Because positive, 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 positive entering, and here dot plus minus, here dot plus minus. There is no problem at all. So please note down. This is actually C and D. You are getting V2. So this is how ideal transform problems can be handled. We'll see in the next session the remaining things.